Welcome to the world of great structures. I'd like to begin this course in an unlikely way, with a short excerpt from Walt Whitman's wonderful poem, Passage to India, written in 1869. Singing my days, singing the great achievements of the present, singing the strong, light works of engineers. Yes, Walt Whitman really did write a poem about engineered works. But what are those strong, light works of engineers anyway? Well, they're the buildings, bridges, and towers that constitute much of our built environment. And as Whitman suggests, the greatest of these should be celebrated as exemplary human achievements, achievements that often define the eras in which they were built. In this course, I hope we can capture some of Walt Whitman's enthusiasm for the strong, light works of engineers, as we explore the great structures of every era from an engineering perspective. Let's begin our journey with a visit to a structure that's indisputably one of the world's greatest, the Brooklyn Bridge. When we look at a magnificent work like this one, we see three essential qualities: form, function, and structure. Perhaps the most obvious of these three is function, how people use the bridge. The function of the Brooklyn Bridge is to span the East River, linking Brooklyn and Manhattan, originally for pedestrians, horse-drawn vehicles, and trolleys, but today for 6 lanes of automobile traffic. Now, back in the 1800s, that function was pretty significant, and the economic and social impacts of linking those two cities was really quite important. Today, however, it's really not the function, but the form that stimulates our emotions and captures our imagination. So what's form? Form refers to aesthetic appeal. The physical features of a building, bridge, or tower, like shape, scale, proportion, ornament. And the form of the Brooklyn Bridge certainly is beautiful. The graceful curve of those main cables, the strength and solidity of the granite towers, that intricate web of steel framework that supports the roadway. You may think of these features as being primarily aesthetic, but there's so much more. They are, in fact, a direct reflection of the scientific principles underlying the design of this great bridge. They are, in a word, structure, a system of load-carrying elements that causes the bridge to stand up. Now, to illustrate this point, I'd like to take a look at a model of a typical suspension bridge. You see here. This model consists of 2 main cables. The cables are anchored out here on the ends. They extend up over the tops of these 2 tall towers, and then they're draped across the main span in that characteristic curved shape. From the cables, you see that I have suspended a series of weights. They're equal weights, and they're all spaced an equal distance apart. So this constitutes a uniform loading on the cable. The shape of the cable, then, is a direct consequence of that loading. It's really a function of physics. The shape of the cable, mathematically speaking, is a parabola, and the parabola occurs specifically as a consequence of that loading. It's science, not aesthetics. Up at the tops of the towers, the cable makes a sharp bend, and as a direct consequence of that bend, all of the tension in the cable is transmitted downward into the towers. And so, in effect, the 2 towers are carrying the entire weight of the bridge and everything that's applied to that bridge in compression directly down through the towers. And that's why on the Brooklyn Bridge, the towers are so massive. They're such robust granite structures. So the parabolic shape of the curve of the cable is caused by the uniform loading. What happens if the loading isn't uniform? What happens, for example, if a heavy vehicle like a train or a heavy truck is crossing the span? Well, when that heavy vehicle gets out here to mid-span, note what happens. Note that the parabolic shape of the cables has now become distorted into something very different. One of the characteristic features of a cable structure is that it changes its shape in response to changes in applied loading. Well, that's all well and good, but if this is a functional suspension bridge, we have a problem, because that sort of distortion in the cable also caused a significant downward deflection of the deck that the vehicles are driving across. So imagine if you're the occupant or driver of a vehicle that's moving from one side of the bridge to the other. When the vehicle's located here, the cable distorts into this shape. As it moves to this location, the cable distorts again, but into a different shape. By the time it gets out to midspan, it's distorted into yet another shape again. And all the while, the bridge is undulating and undergoing all these crazy deformations. Clearly, it's not practical as a functional structure. And that's why most suspension bridges, to include the Brooklyn Bridge, use a secondary structure called a stiffening truss, which is supported directly from the cable. And I do want to emphasize that the stiffening truss is not resting on the towers. Note that there's a space between the ends of the truss and the towers. It's entirely hanging from the cable. But now when I take this same heavy concentrated load of the vehicle crossing the bridge and we place it on the stiffening truss, we see that the shape of the cables didn't change at all. What the stiffening truss does is to distribute that heavy load out laterally so that all of these slender vertical wires, they're called suspenders, carry that load instead of just one or two suspenders, as you saw in the case of the unstiffened deck. So what we see is that all of these prominent aspects of the form of the Brooklyn Bridge, the shape of the cables, the robust stone towers, the stiffening trusses, they all derive from structural purpose. As this demonstration shows, we really can't fully appreciate and understand the Brooklyn Bridge based on its form and its function alone. We need to see and understand its structure as well. Now, this idea of characterizing a constructed work in terms of form, function, and structure, it's not my own, much as I'd like to claim credit for it. We actually owe it to Vitruvius, the great Roman architect engineer of the 1st century BC. And in his book, De Architectura, it's the earliest surviving work on engineering and architecture from ancient times. In that book, Vitruvius asserts that a well-designed building should exhibit three qualities. In Latin, venustas, utilitas, and firmitas. Beauty, usefulness, and strength. Form, function, and structure. So there really is a certain timelessness to this idea. And then again, not everyone agrees with Vitruvius. In 1896, the American architect Louis Sullivan very famously proposed a design philosophy based on the principle that form ever follows function. Now, I'm not an architect, so I won't venture to comment on the validity of form follows function as a design philosophy. But as an engineer, I must protest. Sullivan left out structure. In his essay on this subject, Sullivan makes no mention at all of how structure should relate to form or function. In this course, we will not perpetuate Sullivan's omission. Structure will be the central focus of this course. It'll be the central focus of our study of the world's great buildings, bridges, and towers. What I'm offering you then in this course is an opportunity to engage with our built environment in a fundamentally new way, a more holistic way, and hopefully a more satisfying way, by learning to see and understand structure in the world's greatest buildings, bridges, and towers. Now, this purpose raises three big, fundamental questions that I will be attempting to answer in the remainder of this lecture. First, what is a great structure? That is, what makes a building, bridge, or tower great? Second, what does it take to see structure? And third, what does it take to understand structure? First big question, what makes a building, bridge, or tower great? Well, to formulate a credible answer to this question, I consulted a lot of references. References on great structures, great buildings, great bridges, great architecture, great works of engineering. And while there are a few structures that tend to appear on nearly every author's list in this long reference list, and one of those, by the way, is the Brooklyn Bridge, in fact, there's actually very little agreement beyond a small common core. No two authors that I could find even use the same criteria for greatness. So, under the circumstances, I suggest that we return to the original source of structural wisdom, Vitruvius, who defined the characteristics of a well-designed building as venustas, utilitas, and firmitas. And on that basis, I suggest that a building, bridge, or tower should be considered great if it exhibits exemplary form, function, or structure. Exemplary form, certainly an appropriate criterion for greatness. Let's consider, for example, the Pazzi Chapel, designed by Filippo Brunelleschi, whom we'll meet later on in the course, by the way. It is widely regarded as one of the most perfectly proportioned buildings of the Italian Renaissance. Its function, as Andrea de Pazzi's family chapel, really wasn't particularly noteworthy. And in the mid-15th century, when it was built, those modest-sized domes and vaults are really structurally unexceptional. Yet this architectural jewel is undoubtedly a great building because of its aesthetic quality alone, its sophisticated arrangement of space, its harmonious proportions. Next, exemplary function. Consider the White House, that neoclassical dwelling at 1600 Pennsylvania Avenue in Washington, D.C. It's one of America's best-known and best-loved buildings, but probably wouldn't make anyone's list of great structures except for its function of housing every U.S. president since John Adams. And finally, exemplary structure, our focus in this course. In this category, I'd place structures of unprecedented height or span, as well as those that reflect particularly innovative technological achievements. Consider the Akashi Kaikyo Bridge in Kobe, Japan, a great structure simply because it is currently the world's longest bridge span. Or the CN Tower in Toronto, Canada. It was the world's tallest structure in 1976 when it was originally constructed. And yes, while the CN Tower has now been exceeded by the Burj Khalifa skyscraper in Dubai as the world's tallest structure, the CN Tower should still be considered a great structure, just as the Akashi Kaikyo Bridge should still be considered a great structure, even if someday it's also surpassed in length, because both of these structures met unprecedented structural challenges and constituted unprecedented structural achievements in their own time. In the general category of innovative structures, we might consider, for example, the Iron Bridge at Coalbrookdale, England, which was the world's first all-iron structure constructed in 1779, or the Ingalls Building in Cincinnati, the world's first concrete high-rise structure built in 1903. Both of these structures used new materials and new technologies in a way that profoundly influenced structural engineering in the years after their construction. Okay, now that we've formulated a reasonable set of criteria for greatness, let's move on to the second big question. What does it take to see structure in a building, bridge, or tower? I'd like to begin with a simple observation. The prominence of a structure in a constructed work usually depends on how demanding the structural requirements are. The more demanding the requirements, the more likely that we'll see structure in the resulting constructed product. And really, there are only three different kinds of structural demand: attaining great height, spanning great distances, and also, particularly in modern structures, achieving lightness. That is, using the absolute minimum amount of material necessary to carry loads safely. And when we think about structural lightness, it's useful to think back on Walt Whitman's poem and his reference to the strong, light works of engineers. This idea that we're more likely to see structure when structural demands are high is manifested quite differently in buildings, bridges, and towers. Let's start with bridges. The function of any bridge is to carry people or vehicles either across a body of water or across some area of low ground. This function is an inherently demanding structural requirement spanning a long distance. And so what we see in bridges is that their design is typically dominated by structural concerns. The principal designers of bridges are usually engineers, and structure tends to be quite evident in the constructed product. In most bridges, aesthetics are subordinate to structural concerns if they're considered at all. Let's look, for example, at the magnificent Firth of Forth Bridge in Scotland. It was designed by engineers, John Fowler and Benjamin Baker. And it was designed in response to an extraordinary structural challenge, carrying a railroad across two 1,700-foot-long stretches of open water, the Firth of Forth. The nearby Firth of Tay Bridge had collapsed just 2 years before Fowler and Baker initiated the design for this great bridge. And so the collapse of that bridge was uppermost in their minds as they initiated the design. And so it's understandable that the design of the Firth of Forth Bridge focused fairly heavily on structural strength. As a result, we see that structure is highly visible in the constructed product. Well, as for aesthetics, it depends who you ask. Some people will call the Firth of Forth Bridge beautiful. Others refer to it as spectacularly ugly. In either case, I suspect that Baker and Fowler probably would respond that beauty really was simply beside the point. As we'll see, when we look at this structure in more detail in a later lecture, the unique form of this bridge derives entirely from structural load-carrying principles, not from aesthetic goals. Now, we do occasionally encounter bridges that reflect very high aesthetic aspirations. For example, Santiago Calatrava's Alamillo Bridge in Seville, Spain it's a striking example of a bridge that was designed with very demanding aesthetic goals in mind. Still, the fact that this bridge has to span 600 feet of open water means that structure is as prominent in this bridge as it was in the Firth of Forth Bridge. And indeed, the Alamillo Bridge is beautiful precisely because the shapes, proportions, and arrangement of the structural elements in this great bridge themselves are so incredibly visually compelling. These examples suggest that in great bridges, form follows structure. And seeing structure is usually quite easy. And in fact, that's why bridges are so useful to us in developing our understanding of structure, and that's why you'll see a lot of interesting bridges throughout this course. Next, let's talk about towers. A tower's function is to elevate something. People, church bells, antennas, to elevate those things to a great height. And while towers typically have a significantly higher level of attention to aesthetics in comparison with bridges, because they tend to be visually prominent and they often have a certain symbolic or religious significance, nonetheless, similar to bridges, the function of a tower is really fundamentally structural in nature, that is, raising something to a great height. So we have an inherently demanding structural requirement, and in most towers, therefore, structure tends to be quite evident. Gustave Eiffel designed this iconic tower in Paris with the specific intent of creating the world's tallest structure. And once again, it was an unprecedented structural challenge. The structure, as a result, is quite prominent. First, in the detailed configuration of individual structural members, but also in the overall shape of the structure, which was very explicitly designed to resist wind load. Yes, the structure does have a few non-structural embellishments that Eiffel chose to add. For example, those large semicircular arches that span the lowest level are in fact non-structural elements that Eiffel added both for appearance sake and to enhance public confidence in the strength of the design. But still, on the whole, in the Eiffel Tower, form follows structure. The same could be said for older towers, like the bell tower of the Cathedral of Santa Maria del Fiore in Florence, Italy. Shown here, this campanile, or bell tower, clearly reflects the structural demands imposed by its height and its slenderness. Structure is evident. The hollow, square, tubular configuration of the tower itself, and also in those octagonal buttresses which project from the four corners and add strength to the structure. Now, aesthetics certainly influenced the design of this great landmark. It was, in fact, designed by Giotto, a painter of the Renaissance era. Still, the demands of achieving great height resulted in structure that's both evident and logical. Finally, what about buildings? Well, now the situation's a little different. The principal functions of a building are to enclose space and to facilitate specialized human use of that space. A building is a complex system. Its functions are normally performed by many non-structural subsystems: windows, interior walls, ceilings, lighting, temperature control, and sometimes non-structural exterior walls or cladding. Sure, the structure is always there, holding up the walls and holding up the roof. Yet, because the structural system is but one of many building subsystems, it's often understated or sometimes hidden from view entirely. In a building, the connection between function and structure is less clear, less intimate than in bridges and towers. That's why the principal designers of buildings are usually architects, and engineers design structure in a subordinate role. By the way, this is probably the reason why Louis Sullivan, an architect, didn't include structure in his famous proposition that form follows function. Now, In buildings, the relationship between form and structure tends to be variable, and the visibility of structure varies accordingly. Let's look at some examples. This is Strutt's Mill in Belper, England. Looks like a typical early 19th century textile factory, but the design of this building incorporated a series of structural innovations that were anything but typical. During the Industrial Revolution, a critical need for fireproof construction motivated mill owners to experiment with iron construction. That demand for profitability that was inherent to the industrial enterprise drove an ever greater demand for structural efficiency. And to attain structural efficiency, engineers tried to minimize the amount of iron used in the structure. That resulted in a series of innovations that profoundly influenced structural engineering in the years to come, ultimately leading inexorably to the modern skyscrapers of today. At Strutt's Mill, then, the structural challenge was achieving lightness, the minimum amount of iron necessary to do the job, and there really was little or no attention to aesthetics. The result of this dynamic was a relatively nondescript building, but with an exceptionally sophisticated internal structural system, one, by the way, that we'll look at later in the course. Here, as in bridges and towers, form follows structure. Now, let's consider another great building, the Great Basilica of Hagia Sophia in Constantinople. It was built to satisfy the aesthetic aspirations of the Byzantine Emperor Justinian. And so this building has inspired worshippers for 1,500 years with its vast interior space, crowned by stunning mosaic-encrusted domes, arches, and vaults. But these architectural features, recognize, are also structural elements, which constitute a wonderfully sophisticated structural system that supports that massive central dome that you can see in this image. Seeing structure in this system is a lot more challenging than in Strutt's Mill. As we'll see in Lecture 13 when we look at Hagia Sophia in great detail, there are a number of key structural elements that are part of the system that represent conditions where aesthetic needs were used as the driver for structural innovations in very improbable ways. For example, the central dome of Hagia Sophia rests on a ring of 40 windows around its outer perimeter, located at precisely the location where the greatest amount of structural strength should be. And we'll examine that situation in a little bit more detail in Lecture 13. One of the most amazing buildings of the late 20th century is this one, the Guggenheim Museum in Bilbao, Spain, designed by architect Frank Gehry. This building reflects very high aesthetic aspirations, though not any particularly challenging structural requirements for long spans or great height or light weight. As a result, the structure is entirely invisible, buried within that seemingly random architectural form. At Bilbao, structure follows form, and seeing structure is impossible, at least without a set of construction drawings. The pattern we see in these three examples is that structure is generally more difficult to discern when the aesthetic requirements are greater and the structural demands are relatively less. But lack of visibility doesn't mean that structure is not important in buildings like the Bilbao Guggenheim, or that we can't learn about structure by studying them. Quite the contrary. The structure of the Bilbao Guggenheim is fascinating, precisely because it's so totally distinct from the architectural form. Structural innovation can often be found in the engineer's response to constraint, and there's plenty of constraint in the Guggenheim Bilbao. And so understanding structure in a building is just as important as understanding structure in a bridge or tower. We just need to work a little harder at it, because the building's structure is often less visible in the finished product. Okay, third big question. Now that we know something about seeing structure, what does it take to understand structure? Well, there are three different aspects of structural understanding that I'd like to talk about, and those three aspects actually form the basis for the organization of this course. First, to understand structure, we need to know some fundamental scientific principles governing 6 basic types of structural elements. And these elements are the building blocks that compose nearly all of the world's great structures. The basic types of structural elements are defined in terms of how they carry load. For example, tension members carry load by elongating or stretching in response to applied loads. Columns carry load by shortening in compression. And columns are also characterized by a unique failure mode called buckling, in which the element suddenly displaces laterally in an unstable failure mode that actually is the cause of a number of important structural failures that we'll be talking about later on in the course. Beams carry load by bending or by experiencing flexure. Trusses are structural frameworks that are composed entirely of interconnected triangles, as you can see here, and those members, it turns out, carry load entirely in either tension or compression, normally both. Cable-type structures, as we've seen in our model of the Brooklyn Bridge, are flexible structural elements that carry load principally in tension and change their shape in response to changes in applied load. Again, just as we saw in our Brooklyn Bridge demonstration. And finally, arches. These elements can span horizontal distances, but because of their unique shape and unique supports, they carry load primarily in compression. But in that mode, they're capable of carrying tremendous amounts of load and therefore are the basis for a number of great structures that we'll be looking at in this course. There are also a lot more complex types of structural elements, for example, domes and shells, which really are adaptations or combinations of the basic element types, and we'll be looking at these later on in the course as well. The scientific principles governing these basic structural elements and the materials they're made of are part of engineering mechanics, a branch of the physical sciences that will be the subject of our next 8 lectures. During those 8 lectures, our goal will be to learn how those basic elements work and to see applications of those elements in some of the world's great structures. Okay, the second key aspect of structural understanding is learning to view a building, bridge, or tower as a structural system, an assembly of structural elements interconnected in a way that transmits load safely from element to element all the way down to the ground. We'll be spending lecture 9 focusing on this concept of a structural system, but for now I'd like to just illustrate the basic concept once again by returning to our Brooklyn Bridge model, which happens to be a structural system that incorporates all 6 of the basic structural element types. The way we look at a structural system is to start at the load and to follow the transmission of load from its point of application all the way out to the structural foundations. So here we have our load, the vehicle that's crossing the bridge, and it's being supported directly by the stiffening truss, one of our 6 basic types of structural elements. Down below, the stiffening truss is supported on a series of transverse beams that run across the bridge. Beams, of course, are another of the element types that carry load in flexure. Each beam is supported by a pair of thin cables called suspenders that go from the beam up to the main cable. So the suspenders are tension members which transmit the load up to the main load-carrying elements, the cables. The cables we've already discussed, and they are cable-type structural elements, again, one of the 6. The cables transmit their loads into the towers, and because the towers transmit load in compression, they really function fundamentally as columns. Even though we think of them as towers, structurally speaking, they are in fact columns. And while my model doesn't show it, when you look at the image of the Brooklyn Bridge and its towers, you can see that the towers themselves are pierced by a series of arches which allow the roadway to pass through the bridge. And those arches are important structural elements as well because they create an opening and channel that tremendous amount of compressive load coming down through the towers around the openings and down to the structural foundations. This idea of analyzing a structural system by following the load path down to the foundations, this general approach is going to be the basis for the final 15 lectures of this course as we analyze representative examples of great structures in a series of case studies. These cases are about great structures in their own right, but they're also about developing the skills to see and understand structure. Once you've developed these skills, you'll be able to apply them to any structure. And speaking of understanding structure, we've already talked about 2 of the 3 aspects. The third aspect of structural understanding is historical context, an appreciation for the engineering tools, materials, and technologies that were actually available at the time when the structure was designed and built. For example, We can't fully appreciate the Brooklyn Bridge as an engineering innovation without knowing that it was designed during an era when every single aspect of suspension bridge design and construction was still an unresolved question. I'll conclude this lecture then with one critically important aspect of historical context. From prehistoric times to the present day, the development of engineering design can be viewed in terms of two broad historical periods. The era of empirical design began around 2500 BC, when the very first human activity that could legitimately be called engineering occurred, and it continued through the Renaissance. Throughout this period, design was based entirely on experiences with the successes and failures of previous structures. These experiences were sometimes guided by philosophical or geometric principles, but never by true science. Then, starting with the revolutionary scientific discoveries of the Age of Reason in the 1600s, a new era of science-based design began. It took a long time, about 200 years, but for these new ideas to take hold in engineering practice. But by the mid-1800s, the scientific methods of designing structures were fully established, and they continue today, greatly enhanced by modern computer technologies. Both of these eras have produced their fair share of the world's great structures, from the empirically designed pyramids of 2500 BC to the soaring Burj Khalifa in Dubai, designed with the very latest in modern science-based technology and opened in 2010. What the great structures of the empirical era show us is that science is actually not essential to engineering. Throughout the 4,500-year era of empirical design, the lack of science-based tools didn't prevent ancient, medieval, and Renaissance builders from creating structures of extraordinary form, function, and sophistication. Indeed, as we'll see, the very best of these empirical engineers seem to have developed a keen qualitative sense of structural principles, even if they were ignorant of the quantitative methods. Well, this should be cause for celebration, particularly if you slept through your high school physics class and somehow managed to avoid taking calculus in college. If ancient, medieval, and Renaissance builders learned engineering through experience, then you can too. But although engineering can be learned without science, science can still help us understand structure more broadly, more deeply, and more efficiently. And that's why we'll be learning scientific principles in our next 8 lectures of the course and making use of science throughout the course. I'll explain these points more thoroughly next lecture as we begin our study of engineering mechanics. In the meantime, please recognize that learning scientific principles is not an end in itself, but rather a means to achieve a much greater goal, learning to see and understand structure in the world's great bridges, buildings, and towers. Thank you.